Hello there, and welcome to the Black Hole Files. I'm so glad you've joined me tonight. Whether you're winding down after a long day or just letting your curiosity float before bed. This is our little corner of calm, where science gets soft-spoken, and big questions arrive in their pajamas. Tonight, we're exploring one of the most mysterious threads in the universe. Time. Why does it stretch and shrink, speed up and slow down, even though the clocks keep ticking just the same? We'll travel from ancient stargazers to atomic timekeepers, tiptoe through Einstein's theories, and wonder aloud. What is time, really? And why does it only ever go one way? But before we begin, I'd love to know where you are in the world tonight. What time is it where you are? Drop a comment and tell me your place on the map and your moment on the clock. It's always fun to see how we're scattered across time zones, yet somehow all right here, together, in this very moment. Now, take a deep breath, and let's begin our quiet journey through the mystery of time. 1. What exactly is time? And why does it feel so mysterious and flexible? What is time? At first, this sounds easy. Time is simply the ticking of the clock or the changing of the calendar. We measure time in seconds, minutes, hours, days, and years. But if you think about it, defining time itself is tricky. One way to think of time is the way we label moments in the universe. Just as every page in a book has a number that tells you its order, every moment in time has a label. Like 6 p.m. on June 21st, 2025, for example, that tells us when something happens. In this sense, time is like the page numbers in the story of the universe. It tells us the sequence of events from past to future. Yet, when we try to pin down what time actually is, even scientists scratch their heads. Time is essentially a measure of change. It's how we track things happening one after another. Imagine watching the second hand of a clock go around. Each little tick corresponds to some change. The hand moved. In physics, a basic description is that time is what clocks measure. But that feels like a circular definition. We use time to define clocks, and clocks to define time. Time feels mysterious partly because we can't see or touch it, and we only ever move through it in one direction. We sense time passing as things change. The earth spins and the sun rises and sets. We grow older. A plant sprouts and blooms. But unlike the three dimensions of space, length, width, height, that we can move around in freely, time is like a one-way street. We are all passengers on a time train that never stops and never goes backward. You can remember yesterday, but not tomorrow. Why is that? We'll get to that big arrow of time question later. For now, just note how odd that is. We have a built-in sense of past, present, and future, but we can't reverse that order. This makes time feel almost magical and certainly mysterious. Another reason time is puzzling is that it doesn't always feel steady to us. Have you ever noticed that time can feel stretchy? Think of sitting in a boring class for an hour versus playing your favorite video game for an hour. The same 60 minutes on a clock, but one experience drags and the other zooms by. Time itself, on the clock, hasn't actually changed speed. It's our perception of time that is flexible. Our brains can make a short time feel long and vice versa. Emotions, attention, and context can bend our sense of time. More on that in the next section. This makes time feel personal and a bit mysterious. It's not just an external ticking clock. It's also an experience in our minds. Physicists also found that time can be flexible in the physical world under extreme conditions. According to Einstein, whom we'll discuss in detail soon, time can actually run at different rates depending on how you move or where you are, near a big planet, for example. That's truly mind-bending. It means there's no single universal clock for the whole universe. Time can stretch or shrink like taffy when objects move very fast or feel strong gravity. We don't notice this in everyday life, so time seems absolute to us normally. But the fact that nature allows such flexibility adds to time's mystery. Finally, time is philosophically mysterious. People have long asked, is time real or is it just an illusion? We'll revisit this in Question 8, but even great thinkers like St. Augustine admitted that they know what time is until someone asks them to explain it. In other words, time is so fundamental to how we live that we take it for granted. Yet when we analyze it deeply, it's hard to grasp. To summarize, time is essentially the ongoing sequence of events, the flow from past to present to future, and the way we measure durations. It labels when things happen and keeps everything from occurring all at once. It feels mysterious because we can't hold it or see it directly. We only see its effects, like a clock hand moving or ourselves aging. Time also feels flexible and personal because our perception of it can change with different situations, and even physics tells us time isn't absolutely rigid. All these aspects make time one of the most intriguing concepts we encounter. As one science writer put it, time is obvious until you try to explain it. Then it becomes a profound mystery. 2. Why do we experience time differently? Depending on emotions, age, and situations. Have you ever noticed how time can fly or crawl, depending on what you're doing or how you feel? Our subjective sense of time is very elastic. Let's explore some familiar examples and the science behind them. When you're having fun, time flies. When you're bored, time drags. This is a common experience. An hour at an exciting birthday party might zoom by, while an hour sitting in a dull waiting room feels endless. Why does this happen? Psychologists say it has to do with attention and information processing in our brains. When we're engrossed in an enjoyable activity, we focus on what we're doing and don't pay attention to the clock. Our mind actually processes less extra information because we're absorbed in one thing. With fewer thoughts about anything else, time shrinks in our perception. We look up and surprise. Hours have gone by. In contrast, when we're bored or anxious, our mind wanders and processes a lot of unrelated thoughts, watching the clock, daydreaming, worrying. This high volume of mental chatter makes a short period feel much longer. In short, a busy, focused mind experiences time in fast forward, while an understimulated or uneasy mind plays time in slow motion. This is why an exciting class feels over in a blink, but the last 5 minutes before school ends can feel like forever. Emotions also color our sense of time. Positive emotions, happiness, excitement, tend to make time seem shorter. Time flies when you're having fun is cliché, but it's true. Fun usually means we're focused on the moment and not clock watching. On the other hand, negative emotions like fear or pain can make time feel longer. Think about running on the treadmill and constantly checking the timer because you're uncomfortable. Every minute can feel drawn out. In extreme cases, people report that frightening events seem to occur in slow motion. For example, during an accident or emergency, some people feel like the world slows down. Part of this is memory. We lay down vivid memories during shocks, which later makes it seem slow in recall. But it's also true that during stress, our brain kicks into high gear, taking in lots of information. This increased information processing might stretch subjective time, similar to boredom effect, but caused by adrenaline. So, our emotional state, calm, anxious, joyful, sad, acts like a lens that speeds up or slows down how we experience each moment. Age. Why does childhood feel so long and adulthood so short? Many people feel that as they get older, time seems to pass more quickly. Summer vacations as a kid felt endless, but as an adult they whiz by. There are a few theories for this. One idea is mathematical. Each year you live is a smaller fraction of your total life so far. To a 10-year-old, a year is 10% of their life. That's huge, so it feels long. To a 50-year-old, a year is only 2% of their life, a much smaller slice, so subjectively it feels shorter. Another explanation is about novelty and routine. When you're young, everything is new. Your brain is constantly recording lots of new experiences and memories. First day at a new school, learning new skills, etc. The theory goes that the more memories you form in a period, the longer it feels in hindsight, because you have many frames of reference. Children's brains are like sponges, soaking up tons of details. This rich processing can make time seem to slow down, similar to the boredom mechanism. But in kids, it's because the world is so stimulating and information-rich. As we age, we fall into routines, the same job, same commute, familiar patterns. Fewer new memories are being laid down each day. With less novel information, our perception, especially in hindsight, is that time sped up. In other words, when each day is similar to the last, time seems to blur together and race by. On the flip side, actively seeking new experiences as an adult can make your time feel more full and slow down the blur. Some researchers suggest that trying new hobbies, traveling, learning, basically continuing to challenge your brain, can stretch your sense of time and prevent the feeling that the years are zipping by. Situational focus and multitasking. How we engage with the moment also matters. If you've ever been in a state of flow, deep focus, like when writing a story or playing music, you might lose track of time entirely. Later, you realize hours passed without you noticing. This is related to attention. In a flow state, you narrow your attention so finely that you don't even form the memory of time passing. Thus, it seems to have passed instantaneously. In contrast, if you keep looking at the clock, say you're counting down to the end of a school day, you're very aware of each passing second, which can make it feel longer. There's an old saying, "A watched pot never boils." It humorously means that if you stare at a pot of water waiting for it to boil, it will feel like it's taking forever. Better to distract yourself and it will boil faster in your mind. Let's connect this to science. Our experience of time is highly flexible and subjective. Neuroscientists have found that there's no single time sensor in the brain. Instead, our sense of time is a construction, built from attention, memory, and expectations. Different brain circuits, for emotion, for processing sights and sounds, etc., all feed into how we estimate time. This is why so many factors, emotion, age, novelty, focus, can tweak our timing. Interestingly, some experiments show that the brain's internal clock speed might change with arousal. For example, if you're very scared, your body releases adrenaline, which may make your brain's timing circuits fire faster. In theory, this could make external events appear slower. more frames per second in your brain's camera. When you're relaxed or inattentive, the internal clock may tick slower, and you underestimate duration. These ideas are still being researched, but they align with our everyday observations. To put it simply, time isn't just what the clock says, it's also what our mind says. Physically, a second is always a second. But psychologically, time can stretch like a rubber band or snap back depending on what we're doing and how we feel. This is why an hour in math class may feel longer than an hour playing outside. Our brains are wonderful but subjective timekeepers. Before moving on, here's a neat tip. If you want life to feel longer, in a good way, seek out new and positive experiences. Go on an adventure. Learn a new skill. Visit some place you haven't been. You'll create rich memories, and looking back it will seem like time was nice and full, instead of a thin blur. On the other hand, if you're in a miserable situation, know that your feeling that it's endless is just a trick of the mind. In reality, the same fixed time is passing. Nothing actually makes time speed up or slow down for real, unless we get into relativity, which is another story. It's our perception that changes. Our experience of time is subjective. That's the key idea. So the next time you exclaim, "Wow, time flew," or "This is taking forever," you'll understand why. Emotions, age, and situation are like the DJ that remixes the song of time in our heads. But the cosmic clock keeps ticking steadily in the background, even if our brains dance to a different beat. 3. How did humans first begin measuring time, and why has it become so precise today? Imagine living in the ancient world before smartphones, watches, or even mechanical clocks existed. How would you know what time it is, or when to plant crops, or when to meet someone? Early humans looked to the sky for answers. The cycle of day and night, the phases of the moon, and the changing seasons were the first timekeepers. Let's travel back and see how humans gradually learned to measure time, and then we'll see how we went from simple sundials to ultra-accurate atomic clocks that keep time to the billionth of a second. Early ways of telling time. Day and night, and calendars. The most obvious clock is the sun. Ancient people noticed that days are roughly the same length. The sun rises every morning and sets every evening. They also noticed yearly patterns. For example, colder and warmer seasons, or that certain stars appear at certain times of year. The earliest time measurement was likely just counting days, 3 sleeps from now, and observing seasons for yearly time. At least 5,000 years ago, civilizations like the Babylonians and Egyptians formalized this by creating calendars. They divided time by the natural cycles. The solar day, one rotation of Earth giving day and night. The lunar month, the moon's cycle of phases, approximately 29.5 days. The solar year, the cycle of seasons as Earth orbits the sun, approximately 365 days. Early calendars were lunisolar. For example, Egyptians had a 12-month calendar based on the stars and added extra days to sync with the solar year. Organizing time into days, months, and years allowed communities to plan agriculture, planting and harvest, religious festivals, etc. In fact, large monuments like Stonehenge, circa 2500 BCE, are thought to have functioned as giant calendar markers, aligning with solstices, longest and shortest days, basically a massive clock for the year using the sun's position. Shadow clocks and sundials. Once people had calendars for big spans of time, they also wanted to know the time of day. The ancient Egyptians and others invented devices to divide daytime into smaller parts. One early tool was a shadow stick, an upright stick or obelisk that casts a shadow which moves as the sun moves across the sky. By around 1500 BCE, Egyptians made portable sundials, which were flat pieces with markings and a raised crossbar that cast a shadow. As the shadow moved along the markings, it indicated the hour of the day. Sundials essentially use the sun like the hour hand of a clock. They divided daylight into segments, initially 10 parts plus 2 twilight periods in Egypt, and later 12 hours for day and 12 for night as adopted by Greeks and Romans. Sundials became quite sophisticated. By 300 BCE, there were hemispherical sundials and various designs to adjust for seasons. However, sundials only work when the sun is out. So what about nighttime or cloudy days? Water clocks, clepsydras. To measure time at night or indoors, ancient civilizations developed water clocks. A basic water clock, used by Egyptians and later Greeks around 1500 to 300 BCE, was a bowl or pot with a tiny hole, so that water drips out or in at a steady rate. The pot's interior had markings, and as the water level dropped, it would mark the passing of hours. One found in an Egyptian pharaoh's tomb had marks for each hour of night. The Greeks called these clocks clepsydra, meaning water thief, because the water escaping steals time. Water clocks were among the first timekeepers that didn't rely on the sun or stars. They were used in temples to limit speaking times in courts and even in waking people up. Some water clocks would drop pebbles onto a gong at a set time. Though useful, they weren't extremely accurate. Water flow can vary with temperature and clogging. Still, for centuries, water clocks, sundials, and simple candle clocks, candles marked with lines to burn down at roughly constant speed, were how people kept track of hours. Mechanical clocks. A major leap happened in medieval Europe. By around the 1200s, the first mechanical clocks appeared. These early clocks were often large devices in church towers that used weights, gears, and an escapement mechanism, more on escapement soon, to tick off time. They were motivated by practical needs. Monasteries had strict prayer schedules and city life was getting busier, so a reliable public timekeeper was needed. The word clock comes from clocca, Latin for bell, because these clocks would ring bells on the hour to announce the time to the town. Early mechanical clocks had no minute hand and not always a dial. They often just rang bells. How do they work without electricity? Imagine a heavy weight on a rope. As it slowly drops, it turns gears. That's the power source. The gears transfer the motion into turning clock hands. The critical innovation was the escapement. This is a mechanism that releases the gears in a controlled tick-tock fashion, rather than unwinding all at once. It's like a gate that lets the gears escape a little at a time. An early escapement was a swinging bar, foliot, that rocks back and forth, each swing allowing one gear tooth to move, thus creating a steady interval. This interval became the time unit for the clock's tick. Mechanical clocks allowed for time to be measured in equal hours even at night, and more uniformly than water clocks. By the 14th century, clocks with hour hands were common in European towns. Pendulum clocks. While mechanical clocks were a big improvement, they could be off by, say, 15 minutes a day. Not very precise by today's standards. In 1656, the Dutch scientist Christian Huygens built the first successful pendulum clock, based on prior studies by Galileo. A pendulum, a swinging weight, has a very regular beat. Huygens' clock used a pendulum to regulate the escapement, greatly improving accuracy. Now, clocks could have minute and even-second hands because the mechanism was stable enough to track smaller intervals. With pendulums, clocks could be accurate to within maybe 10 seconds a day, a huge leap. This precision had big implications. For example, accurate timekeeping was vital for navigation at sea. To find longitude, sailors needed to compare local time to a reference time. In the 18th century, John Harrison famously crafted high-precision spring clocks, marine chronometers, that helped solve the longitude problem, saving lives by guiding ships. Time measurement was driving technology and exploration. From pocket watches to quartz watches. Over the 1700s to 1800s, clocks got smaller and more portable. Spring-powered clocks led to pocket watches, which led to wristwatches by the 20th century. Each step required innovations to keep accuracy in a tiny device, jeweled bearings, balance wheels, etc. By the 20th century, the next revolution was using electrical properties for time. Quartz clocks, introduced in the 1920s to 40s, use a tiny crystal of quartz that vibrates when electrified, acting like a very consistent tiny pendulum. It vibrates tens of thousands of times a second. Quartz watches/clocks are far more precise than mechanical ones and need no winding. They paved the way for the timekeeping in all our modern devices. Now, to the second part of the question. Why has timekeeping become so precise today? Do we really need clocks that split seconds into billionths? The answer is yes for our modern technology and science. Here are a few reasons. Scientific curiosity and standards. Scientists always seek to measure things as accurately as possible. Precise time measurement allows experiments in physics. For example, measuring tiny time differences in particle physics or astronomy. It also led to defining the standard units. Today, the second is defined not by Earth's rotation, which is slightly irregular, but by an atomic standard, a cesium atom's vibrations. Specifically, 1 second is defined as exactly 9,192,631,770 vibrations of a cesium atom's microwave frequency. This is because atomic vibrations are extremely consistent, far more than Earth's rotation. By using atoms, we get a universal time standard that any lab in any country can reproduce. Atomic clocks, the ultimate timekeepers. In 1949, the U.S. National Bureau of Standards, now NIST, built the first atomic clock, and by the mid-1950s, cesium atomic clocks were perfected. These clocks tick by using the natural frequency of atoms. The result? Astonishing accuracy. Modern cesium clocks are accurate to about 1 second in 300 million years. And newer research clocks, like optical clocks using strontium atoms, are even better. Some won't lose a second in the entire age of the universe, 15 billion years. In other words, they are so stable that over billions of years they wouldn't drift by even 1 tick. This level of precision is mind-blowing. And it's not just for bragging rights. It underpins a lot of technology. Technology and global coordination. Precise time today is the invisible backbone of many systems. GPS. The global positioning system in your phone or car relies on timing signals from satellites. Those satellites have atomic clocks on board. To find your location, the GPS receiver times how long it takes signals from multiple satellites to reach you. An error of a millionth of a second would translate to hundreds of meters of position error. Atomic clocks on satellites are adjusted for relativistic effects. Yes, Einstein's time dilation, satellites tick a bit faster in weaker gravity and a bit slower due to their motion. Both factors are corrected. Without ultra-precise time sync, GPS would be useless. Communication networks. The Internet, phone networks, and power grids need synchronized timestamps. For example, financial networks need time stamping of transactions to the millisecond or better. Power grids coordinate AC phases across regions. Precise timing helps prevent outages. Data and computing. Every computer has an internal clock, often a quartz crystal, to run processors. For multiple computers to talk, they often sync to atomic clock sources via Internet time servers. Astronomy and space science. Tracking spacecraft, telescopes capturing signals from distant stars, etc., all require synchronized time. If two radio telescopes on different continents observe a distant quasar, they record data time-stamped to the microsecond so that later the data can be combined, interferometry. This gives very high-resolution images of cosmic objects. This technique, very long baseline interferometry, depends on atomic clocks at each telescope. Global time zones and society. As the world became interconnected, think trains in the 1800s, then telecommunications, having a standard precise time became crucial. In the past, each town had its own time, noon when the sun was highest. Once railroads came, this caused chaos. Train schedules need a uniform time. So time zones and standard time were established. Today, Coordinated Universal Time, UTC, is the global standard, kept by a network of atomic clocks around the world. All our local times are offset from UTC. This means wherever you go, time is measured against one ultra-precise heartbeat, provided by atomic clocks. In summary, humans started measuring time with very simple methods: the moving shadows of the sun, dripping water, burning candles. These gave rough divisions of the day. Over millennia, we invented mechanical contraptions with oscillating parts like pendulums to get better precision. And, in the last century, we turned to the fundamental vibrations of atoms, achieving incredible accuracy. We pursued precision partly out of scientific pursuit, to understand the universe, and partly because our modern life demands it: navigation, communication, and coordination. Today, the precision of timekeeping is astonishing. The best clocks are off by less than a billionth of a second per day. One way to appreciate this: NIST's latest atomic clock won't lose or gain a second in 15 billion years. That's longer than the universe has existed. Why would anyone need that? Well, such stability helps test fundamental physics, like whether time itself might vary in different places. So far, it doesn't seem to. And who knows? Future tech like quantum computing or deep space travel might require even finer timing. From counting moons and seasons to vibrating atoms, our timekeeping has evolved hugely. And underlying it is a quest to bring order and predictability to our lives by tracking the mysterious flow of time as closely as we can. It's one of humanity's great achievements that today we can know the time anywhere on Earth to the split second, by simply glancing at a device or listening for a synchronized tick. 4. How did Newton and Einstein's theories change our fundamental understanding of time? For a long time, the concept of time was assumed to be simple. Time flows at a constant rate for everyone, everywhere. This was the common-sense view, and was formalized scientifically by Sir Isaac Newton in the 17th century. Newton imagined time as an absolute tick-tock that marches uniformly throughout the universe. Whether a ball was rolling in London or an apple falling in India, Newton believed there was a single grand clock, so to speak, that kept the same time for both, independent of anything else. Time, in Newton's view, was like a straight line that extends from the infinite past to the infinite future, and it moves forward uniformly. Space, similarly, was an absolute stage, a fixed arena where events happen. This idea is often quoted in Newton's words: absolute, true, and mathematical time, of itself, flows equably without regard to anything external. That's a fancy way of saying time ticks at a constant rate, regardless of who is observing it or what is happening. Humans might measure it differently, with sundials or clocks, but Newton said those are just relative times. Underneath, there's a true time we might not directly sense. This Newtonian view matched everyday experience and worked well with the physics known then. For about 200 years, scientists built on this foundation. Enter Albert Einstein in the early 20th century, who completely upended this idea. Einstein's theories of relativity, special relativity in 1905 and general relativity in 1915, showed that time is not absolute. It can vary for different observers. This was a revolutionary change in our understanding of time, perhaps the biggest since Newton. Let's break it down. Newton's time. Absolute time. Under Newtonian physics, classical mechanics, if 1 second passes for me, 1 second passes for you, and for someone on a rocket, and for someone on Jupiter. Time was thought to be like a universal drumbeat, the same for everyone, everywhere. If two events happen at the same time for me, they happen at the same time for you. In equations of Newtonian physics, time was a background parameter that you could universally synchronize. Another analogy. Newton's time is like a rigid grid that covers the whole universe. Everyone moves through this grid at the same rate. One consequence: Newton considered time separate from space. You have 3D space and a separate 1D time. This common sense persisted because in everyday life we don't notice any differences in how time flows. We aren't usually moving near the speed of light or in extremely strong gravity. Einstein's big idea: relativity. Einstein's theory sprang from a simple yet profound principle. The speed of light is the same for all observers, no matter how they move. To reconcile this and some puzzling experimental results, Einstein proposed that measurements of space and time are relative. They depend on the motion of the observer. In 1905, Einstein published the special theory of relativity, introducing a unified concept of space-time and showing that time can dilate, slow down, and lengths can contract from different perspectives. One famous result is time dilation. If someone is moving at a high speed relative to you, their clock will tick slower compared to yours. This isn't just their clock, it's time itself for them. For example, suppose there are twins. One stays on Earth and the other flies in a fast spaceship. When the traveling twin returns, they will be slightly younger than the Earth twin because less time passed for them. This is not science fiction. It's a real effect, confirmed with airplanes and particles in accelerators. The faster you go, the more pronounced the effect. At everyday speeds it's tiny, but at near light speed it's dramatic. Einstein also found that simultaneity isn't absolute. Two events that appear simultaneous in one frame might occur at different times in another frame. This shattered the idea of a universal now. space and time as one, space-time. Einstein merged space and time into a four-dimensional fabric called space-time. Instead of thinking of time as completely separate from space, he showed they are intertwined. A useful analogy is imagining the universe as a giant loaf of bread, space-time, where each slice is an instant of time, the now across space. Different observers slice the loaf at different angles depending on their motion, so their idea of what events are simultaneous, on the same slice, differs. There isn't one correct slicing, one absolute time. All are valid for that observer. This was a profound shift. Time became flexible and personal to each reference frame, rather than a one-size-fits-all backdrop. General relativity, gravity, and time. In 1915, Einstein extended these ideas to include acceleration and gravity. He showed that gravity is actually the bending of space-time caused by mass. A consequence is gravitational time dilation. Time runs slower in stronger gravity. For instance, a clock on a mountain, weaker gravity, will tick a bit faster than a clock at sea level, stronger gravity, because the one at sea level is deeper in Earth's gravitational well. Again, the difference is tiny for Earth's gravity and normal heights, but measurable with precise clocks. In fact, the clocks on GPS satellites, which orbit high above Earth, tick faster than identical clocks on Earth's surface because of weaker gravity up there. Engineers must correct for this difference so GPS can maintain accuracy. In summary, Einstein's view of time was completely different from Newton's. There is no single absolute time ticking for the entire universe. Time is relative to the observer's state of motion. Moving clocks run slow. From another observer's perspective, this is special relativistic time dilation. Gravity also affects the rate of time. Clocks in stronger gravity run slow compared to clocks in weaker gravity. This was later confirmed by experiments as well, like comparing atomic clocks on Earth's surface versus in airplanes or rockets. Space and time are part of one unified continuum. An event has four coordinates, x, y, z, t, and different observers can disagree on the t and even order of events if they are far apart. But the physics remains consistent through Einstein's formulas. This fundamentally changed how we understand time. Under Newton, time was an unchanging river that flows on its own. Under Einstein, time is more like a stretchy fabric or a dimension that can be warped by motion and mass. It's often said that Newton's time was like a stage on which events happen, while Einstein's time is an actor in the play, interacting with matter and energy. It's hard to overstate how shocking Einstein's idea was at first. Even other scientists took a while to accept it. But experiment after experiment has validated relativity. One early test was observing how fast-moving particles, like muons created by cosmic rays, live longer than they would at rest, exactly because time slows down for them due to their high speed. The airplane clock experiment, Hafael-Keating in 1971, flew atomic clocks around the world on jets. When compared to clocks on the ground, they showed the predicted differences, a tiny fraction of a microsecond, due to their motion and altitude. Today, every time you use GPS, you are implicitly trusting Einstein. Without correcting for relativity, GPS positions would drift by kilometers per day. So, how did these theories change our understanding of time? They turned time from something absolute and separate into something relative and dynamic. We learned that time and space are linked. You cannot fully understand one without the other. Together, they form the space-time fabric of our universe. We discovered that time is personal to your frame of reference. Two observers moving differently will not agree on elapsed time or whether events are simultaneous. This isn't just perspective or illusion. Each is correct in their frame. There is no privileged master clock. We realized that extreme conditions, like near light speed travel or near a black hole, would result in bizarre time effects, like one person experiencing only hours while outside many years pass. Newton would have considered that impossible. Einstein's theory says it's how the universe works. Finally, Einstein's work opened up new questions. If time can bend and warp, could we travel in time or have time loops, as in science fiction? Einstein's equations allow some weird solutions, like wormholes, that suggest maybe, but it's speculative. Newton's framework had no room for that kind of question at all. To illustrate in a simple analogy, under Newton, time was like a metronome ticking steadily in the background. Under Einstein, time is like a rubber band that can stretch or compress depending on how you pull it. Motion, gravity. Both Newton and Einstein agreed that within your own experience, time seems normal. If I'm the one on the spaceship, I don't feel my time slow. My watch ticks normally for me. But Einstein showed that comparing time between different perspectives gets tricky and wonderful. In conclusion, Newton gave us the idea of absolute time, a single, uniform time flow for the cosmos. Einstein overturned this with relative time. Each observer has their own clock and there is no universal now. Time became a dimension in the fabric of reality that can bend with speed and gravity. This paradigm shift was one of the greatest in science. It changed not only physics, enabling technologies and deeper cosmic understanding, but also influenced philosophy and culture. Time travel and the malleability of time became mainstream concepts after Einstein showed time isn't rigid. Our fundamental understanding of time went from absolute to relative, a change that still amazes us today. 5. Why does time only move forward, and could it ever run backwards? One of the most mysterious features of time is that it has a direction. We often call this the arrow of time. We remember the past, but not the future. We grow older, not younger. We see eggs break, but never unbreak. Why is that? The laws of physics in many cases are time-symmetric, meaning if you filmed particles bouncing around and then played the film backward, the basic laws, Newton's, Maxwell's, even Einstein's equations, wouldn't be broken. Yet, in everyday life, time only moves forward toward more disorder, more aging, more knowledge of the past, and none of the future. Let's explore why we experience time as a one-way street, and whether physics allows any loophole for time running backward. The one-way arrow, entropy, and the second law of thermodynamics. The most commonly accepted explanation for the arrow of time comes from thermodynamics, specifically the second law of thermodynamics. This law states that in an isolated system, one that doesn't exchange energy or matter with its surroundings, entropy tends to increase. Entropy is basically a measure of disorder or randomness. Higher entropy means things are more mixed up and disorganized. To put it simply, the universe tends toward messiness. If you don't actively keep things organized, they'll become more disordered over time. A clean room gets messy. A hot cup of coffee left out cools down, spreading its heat to the room. Ice melts into water, etc. It's easy to go from organized to messy, but extremely hard to go the other way without effort. Now, how does this relate to time moving forward? The idea, proposed by physicist Ludwig Boltzmann in the 19th century, is that the forward direction of time is the direction of increasing entropy. The arrow of time points from lower entropy, the past, to higher entropy, the future. For example, consider an egg. In a low entropy state, it's unbroken, yolk and white neatly inside the shell. Drop the egg, it splatters. Now it's a high entropy state. The contents are all mixed and spread out, a big mess. Physics could run backwards in theory. There's no law saying the yolk cannot unscramble, but it's so incredibly improbable that we never see it. There are vastly more ways for the egg's molecules to be in a disordered, splattered arrangement than in a neatly ordered, unbroken arrangement. So, statistically, the egg will never spontaneously reassemble. It would violate the tendency toward higher entropy. Thus, we only see eggs breaking, forward time, and never the reverse. Think of another example. If you pour milk into coffee, initially the milk is separated, low entropy in the sense of two distinct regions. Very quickly, the milk and coffee mix into a uniform light brown, higher entropy, more mixed. You'll never see the milk spontaneously separate out from the coffee on its own. That would be time running backward from the perspective of entropy. In summary, time moves forward because that's the direction toward more entropy, and that matches our everyday observations. If someone showed you a film of a broken glass reassembling itself and jumping back onto a table, you'd immediately suspect it's being played backward, because that kind of decrease in entropy just doesn't happen naturally. In the forward direction, we see the glass fall and shatter. Order, disorder, entropy up, which feels normal. It's important to note that this argument is statistical. It's possible, in a microscopic sense, for entropy to decrease in a small system for a short time, but exceedingly unlikely in a large system. With zillions of atoms, the odds of all random motions reversing neatly is astronomically low. So, for practical purposes, it's effectively impossible to see time reverse in terms of macroscopic phenomena. This gives time a built-in arrow, from the past, more ordered, to the future, less ordered. Other arrows and the uniqueness of forward. There are other arrows of time that align with the thermodynamic arrow, the psychological arrow of time. We remember the past and not the future. Our memory formation process and causality in our brains works in one direction. This likely is because forming a memory increases entropy in the brain. Laying down a memory trace uses energy, dissipates heat, and you can't remember something that hasn't happened. If time ran backward, presumably we'd recall the future, which sounds nonsensical to us. The causal arrow. Causes precede effects. You light a match. Cause, then you get a flame. Effect, not vice versa. If time reversed, effects would come before causes. Flame appears and then match strikes, which breaks everything we understand about logic and physics. The radiative arrow. If you drop a pebble in a pond, waves spread outward. They don't all suddenly converge and eject the pebble back to your hand. Many processes, sound, light, physical disturbances, tend to move outward and dissipate, not spontaneously concentrate. This is another reflection of entropy increase, energy dispersing. Interestingly, most fundamental physics laws don't pick a time direction. Newton's laws, electromagnetism, etc., work mathematically even if you replace T by negative to negative t, a movie of planets orbiting works in reverse too. However, when you add the second law and the special initial conditions of our universe, we believe the universe started in a low entropy state, e.g., the Big Bang was a very hot but relatively orderly state. You get an arrow. The Big Bang idea implies that at the beginning, entropy was extremely low. Perhaps all matter, or energy, was concentrated. As the universe expanded, entropy increases. Stars burn fuel, making heat, higher entropy. Structures form and eventually decay. The universe as a whole is moving from a highly ordered initial state to a high entropy state, sometimes poetically described as a future heat death, when entropy is maximal and no useful energy remains. That sets the direction of time's arrow on a cosmic scale. So, time moves forward because the universe started with order and is progressing towards disorder. Every tick of the clock, every natural process, is part of that gradual march toward higher entropy. Could time ever run backwards? This is a fun but tricky question. In principle, the laws of physics don't forbid time reversal for small-scale interactions. If you had an isolated system of a few particles, it's possible, though incredibly unlikely, that all their motions could invert and retrace exactly, effectively going back in time for that system. But for anything complex, the odds are essentially zero. From a practical standpoint in everyday conditions, we have never observed time reverse. To have time run backward around us, all processes would have to reverse. Shattered glass pieces would assemble. Smoke would go back into a fire. People would get younger, etc. This would require a massive decrease in entropy everywhere simultaneously, which conflicts with the second law and the fact that it's overwhelmingly improbable. Could some weird physics allow backwards time travel or reversed time flow? This enters speculative territory. Time travel and relativity. Einstein's theory of general relativity does allow some solutions, like certain space-time geometries, where you could have closed time-like curves, essentially loops in time. The idea of a wormhole is often mentioned, a shortcut through space-time that, in some configurations, might let you come out in the past. However, these are highly theoretical. Most physicists suspect that quantum effects would prevent actual time travel paradoxes. Stephen Hawking even proposed a chronology protection conjecture. Basically, natural laws might conspire to prevent macroscopic time travel into the past. For instance, a wormhole that might allow backwards travel would self-destruct due to feedback, etc. And indeed, we don't see tourists from the future among us, which suggests backward time travel isn't happening, at least not in any obvious way. CPT symmetry in particle physics. There is a symmetry in physics if you invert charge, parity, mirror space, and time together. Many processes look the same under CPT, but no known process shows just t, time reversal on its own in full. Except some quantum interactions show a tiny asymmetry that actually does distinguish past versus future, related to the weak nuclear force and CP violation. Interestingly, this slight CP violation in particle physics might connect to why there's more matter than antimatter in the universe, and it also technically gives an arrow, but that's beyond 8th grade scope and a very subtle effect. Quantum mechanics and time. There are interpretations of quantum physics that suggest time might be symmetric at a fundamental level, and the arrow comes in only when you consider big systems, due to entropy and the collapse of wave functions, etc. Some speculative quantum gravity theories even suggest time could be an emergent illusion, which we discuss more in the next question. But none of these allow an everyday person to experience backward time. For a young student-friendly analogy, imagine time is like a river. It flows in one direction because it's all going downhill from an initial high ground, low entropy, to a lower ground, high entropy. It's theoretically possible to see a little eddy in the river that flows backward locally, but the river as a whole won't reverse and flow uphill. Could we ever reverse time locally? Scientists have thought, if you could somehow decrease entropy in a system, you could make that system's arrow reverse. But decreasing entropy requires work, energy input somewhere else, thus increasing entropy elsewhere. For example, a refrigerator pumps heat out of its interior, making inside more ordered, lower entropy, but dumps heat into the room. Net entropy increases in room plus fridge. You can locally reverse entropy, make something cold or separate mixtures, but at the cost of greater entropy generated outside. So you can't globally reverse time's arrow. Science fiction aside, all evidence says time only runs forward for us. We can slow our personal passage through time by going fast or using gravity. Relativity can make you travel to the future faster than those you left behind. But going to the past is another matter entirely. Most scientists would say backward time travel is highly implausible, if not impossible, because it messes with causality, the cause-effect order, and would require conditions not found naturally, exotic matter or energy distributions to warp space-time. In summary, time moves forward because of entropy. The universe's tendency to go from order to disorder gives time a direction. The past is low entropy, neatly arranged. The future is high entropy, spread out and mixed up. This arrow aligns with everything we experience: broken eggs, mixing drinks, aging, memory. As for running backwards, physics doesn't show any mechanism for reversing the entropy of the whole universe. Unless some new physics is discovered, and so far none has indicated reversible macroscopic time, time reversal remains a fantasy. So we're all stuck moving forward in time together, witnessing more interesting things get messy, and remembering when they were neat. The arrow of time is one way, at least in our universe as we know it. 6. What does quantum mechanics suggest about the true nature of time? Quantum mechanics is the branch of physics that deals with the very small, atoms and subatomic particles, and it's famously weird. When we ask what quantum mechanics suggests about the nature of time, we enter a realm of speculation and deep theory, because even physicists are still trying to figure this out. However, we can discuss a few intriguing ideas from quantum physics and how they might change our perspective on time. First, it's important to note that quantum mechanics and our everyday experience of time can feel at odds. In our daily life and in classical physics, we think of time as continuously flowing and universally shared. But quantum mechanics and relativity combined hint that our intuitive picture might be incomplete. 1. Quantum mechanics treats time differently than relativity. In standard quantum mechanics, the kind developed in the early 20th century, time is treated as an ordinary background parameter, kind of like Newton's absolute time in some ways. Schrödinger's equation, which describes how a quantum system's wave function evolves, uses time t as a variable that flows uniformly. Unlike position or momentum, which are represented by operators in quantum theory and have uncertainty, time in basic quantum theory is not an operator. It's just part of the backdrop that everything is measured against. This means that quantum mechanics, by itself, doesn't question time's flow. It basically assumes time is there, ticking away as we measure how a particle's probability distribution changes. However, general relativity, Einstein's theory of gravity, tells us time is flexible, part of space-time, and can be warped. So we have a bit of a conflict. Quantum physics usually assumes a fixed stage for time, while relativity says the stage itself is dynamic and can bend. This mismatch is one aspect of the famous problem of reconciling quantum mechanics with gravity, the search for a theory of quantum gravity. It suggests that our understanding of time is incomplete. We can't fully describe time at the quantum level until we merge these theories. 2. The problem of time in physics. Researchers actually speak of a problem of time in trying to make quantum mechanics and general relativity play nice. In a yet-to-be-found quantum theory of gravity, like maybe a theory of everything, our usual notion of time might need revision. Some proposals suggest that on the smallest scales, like the Planck scale, far smaller than atoms, time might not even be a well-defined continuous flow. It could be grainy or emergent from something more fundamental. One radical idea is that time might not be a fundamental property of the universe at all, but something that emerges from quantum correlations. This sounds crazy. How can time not be fundamental? To understand that, consider how temperature is not fundamental at the microscopic level. Individual atoms don't have a temperature, but a large collection does. Temperature emerges from many particles' motions. Analogously, some physicists speculate that time might emerge from the entanglement and states of quantum particles, rather than being fundamental. 3. Time as an emergent phenomenon. Quantum entanglement idea. A recent line of research suggests that time might arise from quantum entanglement. Entanglement is the mysterious quantum link that can exist between particles. They share a combined state such that what happens to one instantly influences the other, no matter how far apart, within the rules of quantum probability. A study, as mentioned in 2024 News, proposed that if you have a quantum system and a clock system entangled with each other, time emerges for the system relative to the clock. But if a system were completely isolated with no entanglement to anything, no external clock, it might not experience time. It would be like it's frozen with no change. In other words, time could be a byproduct of quantum relationships between objects, not a built-in stage. This is a very abstract concept and still hypothetical, but it hints that at the deepest level, time might not be a standalone entity. To phrase it more simply, some scientists think time might emerge when things interact. If a particle has nothing to interact with, does it even experience time? Possibly not in these interpretations. This challenges the everyday notion that time is always ticking. It suggests time might be like a pulse that arises from interactions, like the ticking of a clock requires the clock mechanism. No mechanism, no tick. 4. Quantum uncertainty and time. In quantum mechanics, we have the famous uncertainty principle. You can't precisely know certain pairs of properties at the same time, like position and momentum. There is also an energy-time uncertainty principle. You can't measure energy precisely in a very short time interval, and vice versa. This isn't exactly the same as position-momentum uncertainty. Time isn't an operator. But it implies there's a fuzziness in temporal measurements for quantum events. For example, very short-lived particles that exist only fleetingly have uncertain energies. This can be thought of as borrowing energy for a short time, a concept behind virtual particles that pop in and out of existence briefly. In quantum physics, empty space isn't truly empty. Particles can briefly appear and disappear as long as they vanish within a time allowed by the energy-time uncertainty. This suggests that on tiny scales, the distinction of before-after can get blurry. Quantum fluctuations don't follow smooth, classical timelines. 5. Does quantum mechanics allow time reversal or influencing the past? Generally, standard quantum mechanics doesn't let you send information to the past or anything like that. It respects causality on the macro level. However, there are some interesting quantum phenomena. Quantum entanglement. It can create correlations that are felt instantaneously, at least no detectable time delay, across distance. This does not allow sending usable messages faster than light or back in time. It's just correlated randomness when measured. But it is as if two particles share a state that transcends normal space-time separation. Some have wondered if entanglement hints that our linear time view is incomplete. The entangled particles seem connected outside of normal time flow. Einstein himself was puzzled by this spooky action at a distance. We now understand it as part of quantum theory's non-local nature, but it doesn't break time's arrow. It just is an odd feature. Retrocausality? There are interpretations of quantum mechanics, like the transactional interpretation, that are time-symmetric and involve waves going forward and backward in time that form a sort of handshake. In this interpretation, an emitter and absorber of a particle exchange advanced, forward in time, and retarded, backward in time, waves. The result is what we see as a normal causal transaction. This is a bit philosophical. No experiment has shown true backward causation. It's more a mathematical interpretation to make the equations time-symmetric. Quantum loops in time. Some theoretical proposals, often involving quantum gravity or speculative scenarios, consider whether closed time-like curves, time loops, could exist at quantum scales. If they did, quantum mechanics would have to handle consistency, like avoiding paradoxes. This is very speculative. No evidence for such loops exists. 6. Does quantum mechanics say time is an illusion? You might have heard statements like, time is an illusion, or time isn't real from some physicists. What they often mean is that at the fundamental level, the equations can be time-symmetric or time doesn't appear as a fundamental parameter in some advanced formulations. For example, in the Wheeler-DeWitt equation, an attempt in quantum gravity, time doesn't even appear. It's called the timeless equation of the universe. This suggests that on the most fundamental level of reality, time as we know it might not exist. Instead, it emerges when we look at large classical systems. A simplified analogy: think of a flipbook of drawings. Each page by itself has no motion, no time. But when you flip them, motion emerges. Some think reality might be composed of many possible snapshots, quantum states, and time emerges from transitioning through them in sequence due to how observers experience them. All this can be quite head-spinning, even for adults. For an 8th grade level takeaway, quantum mechanics introduces a world where the classical idea of a smooth, universal time is challenged. It suggests that our usual idea of time might break down at tiny scales or need rethinking. For instance, time might not be fundamental but something that comes about when lots of particles interact. It also shows that trying to combine the theory of the very small, quantum, with the theory of the very big, relativity, is tricky, and the concept of time is at the heart of that trickiness. Some scientists are actively researching if something deeper underlies what we call time, possibly using quantum experiments. To tie it to something tangible, atomic clocks are a quantum device using the energy transitions of atoms. Their extreme precision, as we discussed in Question 3, actually helped confirm Einstein's relativity, time dilation. But from a quantum view, an atomic clock ticks by electrons jumping between energy levels, absorbing, emitting photons of certain frequency. If time were to behave weirdly at quantum scale, it might affect even these basic processes. So far, atomic clocks behave exactly as expected, with a steady ticking according to quantum rules plus relativity. That means whatever odd nature time has in quantum theory, it still produces a consistent flow when averaged out. In summary, quantum mechanics suggests that time might not be as straightforward as we think. It might emerge from a deeper reality rather than be fundamental. There is an unresolved conflict between quantum theory's use of time and relativity's concept of time, pointing to the need for a new understanding, quantum gravity. Time at tiny scales could be fuzzy or behave nonlinearly, but when we zoom out, it looks smooth. While quantum physics doesn't let us rewind time or send signals to the past, it does force us to question, what is time, really? Perhaps more than any other field of science. So, the true nature of time according to quantum mechanics is still an open question. Some even say time might be an illusion or emergent phenomenon in the quantum world. What we do know is that time in the quantum realm is likely not a simple universal tick-tock. It's tied up with observation, entanglement, and the fundamental structure of space-time. The more scientists explore quantum reality, the more mysterious time appears, which is both frustrating and exciting. Who knows? The next great breakthrough in physics might come from figuring out how time really works at the smallest scales. 7. How do our bodies keep track of time? And why does it affect our health and behavior? You might have noticed that you tend to feel sleepy at night and awake during the day, or that you get hungry around the same times each day. This isn't just habit, it's driven by your biological clock. Humans, and almost all living things, have internal timing systems. Let's explore how our bodies keep track of time and why this is so important for our health and daily behavior. Our body's internal clock, the circadian rhythm. Circadian rhythm is the scientific term for the roughly 24-hour cycle our bodies follow. In fact, circadian comes from Latin circadium, meaning about a day. Almost every cell in your body has some clock-like activity, but the master clock is in your brain. There's a small region in the brain called the suprachiasmatic nucleus, SCN, a tiny cluster of about 20,000 neurons, located in the hypothalamus, deep in the brain. This SCN is like the conductor of an orchestra, making sure all the body's functions are in sync on a 24-hour schedule. Human circadian rhythm over 24 hours, showing changes in a person's physiology and behavior at different times of day: morning, afternoon, evening, night. Our internal clock coordinates things like the sleep-wake cycle, body temperature, hormone levels, and even digestion on a roughly 24-hour schedule. Disruptions to this cycle, like staying up late or shift work, can throw our systems off balance. How does the SCN know what time it is? Light is the main cue. There are special cells in our eyes that send signals directly to the SCN when they detect light. In the morning, when light enters your eyes at sunrise, or when you turn on lights, it triggers the SCN to reset and say, "It's daytime." The SCN then coordinates a host of responses. It signals for certain hormones to be produced or suppressed. For instance, melatonin, a hormone that makes you sleepy, is produced at night in darkness. Light hitting the eyes stops melatonin production. That's why looking at bright screens at midnight can make it harder to sleep. It's suppressing melatonin by fooling your brain into thinking it's daytime. It affects body temperature. Your body temp rises during the day and falls at night as part of preparing for sleep. It influences the digestive system and metabolism. Your body is primed to eat during the day and digest food efficiently then, whereas late at night those processes slow down. It even affects things like blood pressure and reaction time. For example, many people have a peak in alertness in late morning and a small slump in the early afternoon. All these daily cycles are part of the circadian rhythm orchestrated by the SCN and the clock genes in our cells. Yes, there are actual genes, first discovered in fruit flies, that create proteins on a roughly 24-hour cycle, providing a molecular basis for the clock. In short, our bodies keep time by a combination of genetic mechanisms, biochemical clocks, and environmental cues, especially light and darkness. The SCN in the brain is like the master gear that sets the schedule, and it syncs up with light signals each day to stay accurate, similar to how you might reset a watch to the correct time each day if it drifts. Effects on health and behavior. Because our internal clock regulates so much, disrupting it can have noticeable effects. Here are some ways our circadian rhythm, or its disturbance, impacts us. Sleep-wake cycle. This is the most obvious. The clock causes melatonin to rise in the evening, making you sleepy, and cortisol to rise in the morning, helping you feel alert. If you follow a regular schedule, you'll tend to get sleepy around the same time each night and wake up around the same time. When you force a different schedule, it can be hard. For example, teenagers often experience a natural shift where their clocks run a bit later. They may not get sleepy until later at night and want to wake up later. This is a normal developmental change, and one reason early school start times can be rough on teens. In contrast, many older adults find themselves getting sleepy earlier and waking up earlier as they age. Jet lag. If you've ever traveled across several time zones, you likely felt jet lag. That's when your internal clock is still synced to your old time zone and not the new one. For example, you fly from London to New York. When it's bedtime in New York, your body might feel like it's 5 a.m., London time, making it hard to sleep. Symptoms include fatigue, insomnia, digestive problems, all because your body's various processes are out of sync with the local time. It usually takes a few days for the SCN and body clocks to adjust to the new light schedule. Jet lag is a clear demonstration of how strongly our body follows its internal time and how health and alertness suffer when it's misaligned. Shift work and health. People who work night shifts or rotating shifts, like nurses, factory workers, etc., often have to be awake and active at night and sleep in the day, which is opposite the natural cycle. This chronic misalignment can cause various issues. In the short term, it can lead to sleep problems, tiredness, and digestive troubles, since you're eating at odd times against your biological day. In the long term, studies have found that long-term shift work is associated with higher risks of certain health problems like heart disease, obesity, and diabetes, as well as mood disturbances. The body isn't necessarily designed to be in active mode at night. Hormone releases, insulin sensitivity, etc., all follow a day-night pattern, and flipping that repeatedly can strain the system. Daily performance and behavior. Ever notice that you feel more alert at certain times of day? Most people have a surge of alertness a couple of hours after waking, mid-morning, and might feel a dip in the early afternoon, the post-lunch slump. This isn't just due to lunch, it's partly circadian. Our reaction time, coordination, and even mood can fluctuate on a 24-hour cycle. For example, athletics research shows many athletes perform best in late afternoon when body temperature is highest and muscles are warmed up. And in many cultures, an afternoon nap, siesta, evolved likely because of that natural dip in alertness in early afternoon. Mental health. There's a link between circadian rhythms and mental health. Disrupted sleep and irregular circadian rhythms can contribute to depression or anxiety in some people. Also, some disorders like seasonal affective disorder, SAD, a type of depression in winter, are related to changes in light exposure and thus circadian rhythm. Shorter daylight can mess with the clock for susceptible people. Light therapy, sitting by a bright lamp in morning, is often used to help SAD, essentially giving the body a stronger light cue to set the clock properly. Immune function and cell repair. Our body even times certain repair processes to happen during sleep. For instance, cell repair and growth hormone release happen mostly at night during deep sleep. The immune system's activity can vary. Some research suggests we might fight infection better at certain times. So, pulling an all-nighter not only makes you tired, it might reduce your body's healing and defense mechanisms. Why does messing with the clock cause these issues? Because our bodies expect a stable rhythm. Every cell's chemistry is tuned to a schedule. Enzymes go up and down, organs cycle through active and rest phases. When everything is synchronized, like instruments in an orchestra playing in time, you feel good and your body functions optimally. If things get out of sync, imagine half the orchestra playing off-beat. You get biological chaos. Sleep problems, digestive issues, feeling cranky or unfocused. Cool facts. Babies and clocks. Newborn babies don't have a well-formed circadian rhythm for the first few weeks, which is why they wake up around the clock. Their hormones and temperature rhythms haven't settled. By a few months old, they start producing melatonin and cortisol on a schedule and sleep longer at night. Parents rejoice as the baby's clock aligns with day-night. Chronotypes. Night owls versus morning larks. Not everyone's clock is the same. Some people naturally wake up early and are most alert in the morning. Larks. Others get a second wind at night and prefer sleeping late. Owls. These traits are partly genetic. So, your friend who can't function before 10 a.m. isn't just lazy. They might have a biological clock that runs a bit later. Unfortunately, society, work or school times, often favors morning people, which can be a challenge for night owls. Beyond 24 hours. If humans are put in a bunker with no external cues, no sunlight, no clocks, interestingly, their internal day might drift to around 24.5 hours or so on average. In experiments, people tended to go to bed a bit later each day in the absence of light cues. Our natural rhythm isn't exactly 24 hours, but slightly over. Sunlight resets us daily to 24 hours. Some other animals have different periods. For instance, Certain mice might have a 23.5-hour rhythm, etc. Each species differs. Other cycles. While circadian, 24 hours, is the main one, our bodies also have longer and shorter rhythms. For example, hormone cycles, like the female menstrual cycle, 28 days, or ultradian rhythms, like the 90-minute cycles of sleep stages during sleep, or even patterns in attention that cycle multiple times per day. In summary, our bodies keep time via an internal clock system centered in the brain, suprachiasmatic nucleus, that synchronizes to light and other daily cues. This circadian clock orchestrates daily changes in hormones, alertness, temperature, and organ functions. Living in tune with this rhythm, regular sleep times, regular meal times, getting morning sunlight, generally helps us feel our best. When the rhythm is thrown off by travel across time zones, by staying up all night, by irregular schedules, we feel out of sorts because our internal processes are no longer in sync with each other or with the external day-night cycle. In the long run, keeping odd hours can stress our systems and affect our health. That's why sleep doctors advise maintaining a consistent sleep schedule and getting daylight exposure in the morning. It keeps your internal clock aligned correctly. Our body clock is a marvel. It's like we have an inner timekeeper ticking away, making sure the right things happen at the right time. It's one more way we are connected to the natural cycle of day and night. So, the next time you feel drowsy at 10 p.m. or wake up hungry for breakfast, you can thank your biological clock for keeping time for you. 8. Can we actually travel through time? And does time really exist at all? These are two of the most fascinating questions about time. Time travel has been a staple of science fiction and daydreams. Who wouldn't want to visit the future or change the past? And the very nature of time, whether it exists as we think it does, ventures into deep philosophical and scientific territory. Let's tackle them one by one. Time travel. Is it possible? Traveling to the future. Good news. Traveling into the future is actually possible. And we all do it, at 1 second per second. But jokes aside, Einstein's theory of relativity indeed allows a form of one-way time travel to the future. As we discussed, if you move at extremely high speeds or stay near a strong gravitational field, time will pass slower for you relative to someone who stays put. So, when you return to that someone, you will have experienced less time. Effectively, you've jumped into their future. This is known as the twin paradox scenario. One twin flies in a fast rocket, comes back and finds the Earth twin has aged much more. It's been experimentally verified on small scales, with fast-moving planes and atomic clocks, that this time dilation is real. Astronauts on the space station, for example, age a tiny bit less than we do on Earth because they are moving fast and also a bit further from Earth's gravity. After a year in orbit, an astronaut might be a few milliseconds younger than they would have been on Earth. This is real-life future travel, albeit by very small amounts. If we had technology to go close to light speed, we could, in principle, leap far into the future. Imagine a spaceship that goes near light speed to a star and back. For the travelers, perhaps only 1 year passes, but back on Earth maybe 10 years have passed. They land essentially 9 years in Earth's future from their perspective. The catch is, we currently can't reach anything close to such speeds with human travel, and there are engineering and energy limits. But the physics says it's allowed. It's just a matter of technology. Another way to future travel is using gravity. If you could sit near something like a black hole without getting destroyed, time would go slower for you due to intense gravity, gravitational time dilation. Then you come back to Earth and more time has elapsed here. Again, practically reaching a black hole is extremely difficult, and surviving near it is another story. But conceptually, future travel is fine with physics. So, yes, time travel to the future is not only possible, it's basically unavoidable by relativity. Moving clocks will experience less time. It's one way, though. You can't use the same mechanism to go back to where you started in time. Traveling to the past. This is the tricky and most likely impossible part. None of the physics we know allows you to go back in time and alter events or meet your past self. The arrow of time and causality, cause-arrow effect, seem to hold firm. If backward time travel were possible, it introduces paradoxes, like the famous grandfather paradox. What if you go back and accidentally prevent your grandparents from meeting? Then you wouldn't exist to go back. Such paradoxes make most scientists think nature has some built-in protection against backwards time travel. General relativity does have weird solutions like wormholes or spinning universes, Gödel's solution, that mathematically allow paths that go back in time. A wormhole is a hypothetical tunnel through space-time that could connect two distant points in space and time. In theory, if one mouth of a wormhole is moved at high speed, time dilated, and brought back, it could be out of sync with the other mouth, potentially allowing an object entering one mouth to come out of the other at an earlier time than it entered. This is highly speculative and would require exotic matter with negative energy to keep a wormhole open, which we've never seen. Most physicists suspect that quantum effects would destabilize any would-be time travel wormhole. No experiment or observation has shown any evidence of closed time loops. Stephen Hawking once quipped that the absence of tourists from the future is an argument against time travel to the past. If people will invent time machines in the far future, why haven't we seen any time tourists popping up? Maybe they're hiding, or maybe it's just not possible. Hawking proposed a chronology protection conjecture. The universe won't allow time machines. From a simpler standpoint, every known physical process respects cause and effect. Even quantum processes, which are probabilistic, don't allow you to send a message back in time. For example, you can't have an effect, like a wave, without a cause preceding it, like dropping a stone. Reversing time would break this order in potentially chaotic ways. So, the mainstream scientific view: no, we cannot travel to the past, at least not in any macroscopic, controllable way. Backwards time travel is likely impossible because it would violate fundamental causality and require conditions not known to exist, like traversable wormholes or infinitely long spinning cylinders in space, etc., none of which we have. What about the far future? Could advanced civilizations figure out something we haven't? It's speculative. Some have suggested if the universe had exotic geometries, or if you could manipulate space-time in extreme ways, using black holes, cosmic strings, etc. Maybe there's a loophole. But even if a loophole exists, paradoxes imply something weird must happen, like the multiverse theory. Maybe going back in time creates a parallel universe branch so you can't affect the one you came from. These ideas veer into speculation and aren't supported by evidence. In summary on time travel, going forward in time, yes, easy, just live, or go fast to do it faster. Going backward in time, extremely doubtful according to known science. At least for now, the past is untouchable history. Does time really exist, or is it an illusion? This question is more philosophical. We experience time very strongly. Every moment we sense time passing. But some physicists and philosophers argue that time might not be fundamentally real in the way we think. One idea in physics is the block universe, or eternalism. According to Einstein's relativity, as we discussed, there isn't a single universal now. All moments in time, past, present, future, can be seen as coexisting in a four-dimensional space-time block. In this view, time is like a spatial dimension, just another direction. The past and future are there, just like the left and right side of a loaf of bread are there. We happen to perceive one moment, now, but that's similar to how we might see one slice of the loaf at a time. Einstein himself, in a letter consoling a friend about death, wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion." He meant that from the viewpoint of physics, each moment in time is as real as any other, and time doesn't flow. It just is. Our consciousness moves through this block and gives the impression of flow. On the other hand, there's presentism, the philosophical idea that only the present moment is real. The past is gone. The future hasn't happened. Presentism aligns with our intuition, but is hard to reconcile with relativity, which doesn't designate a single universal present for everyone. Some modern physics approaches, especially in quantum gravity, suggest time might not be fundamental. For example, in attempts to unify quantum mechanics and general relativity, time sometimes disappears from the fundamental equations. The Wheeler-DeWitt equation in quantum cosmology basically says the universe's state doesn't evolve in time. It's static. This implies that what we call time might emerge from some deeper timeless reality, when we have many particles or an observer to experience change. One might ask, if time is an illusion, why do we experience it so vividly? There are various thoughts. Perhaps our brains have evolved to sense time as flowing because it's useful for survival. We needed to predict and remember. Maybe what we call the flow of time is tied to entropy and memory. We remember the low entropy past and not the future, giving an impression of flow in one direction. It could be that time at a fundamental level doesn't pass. Instead, the entire history of the universe is laid out, and we just perceive it sequentially. From a practical standpoint, time certainly exists as a parameter in equations and as something we measure with clocks. But the question might be hinting, is time something that is out there, like an entity, or is it just a concept we use to track change? Some philosophers argue that time is just a measure of change. If nothing changed in the universe, would time be meaningful? Probably not, because time is evidenced by change. Clocks ticking, hearts beating, planets moving. In that sense, time could be secondary, a way to sequence events. In classical physics, time was absolute and real, Newton's view. In relativity, time is part of space-time, real but relative. In some quantum views, time might not be fundamental at all, just a convenient parameter that emerges. Another perspective is psychological. Maybe time is partly a construct of our minds. We seem to experience a present moment moving forward. Some neuroscientists study how the brain perceives time. It might chunk things into perceptual moments, etc. This doesn't deny physical time, but it shows our experience of time can be subjective. as we saw with perception in question 2. To directly answer, does time really exist at all? Most physicists would say yes. Time exists in that it's part of the fabric of reality, especially since relativity, time is literally intertwined with space. But what it is exactly is still debated. Is time fundamental or emergent? Is the flow of time an illusion, with past and future equally real, or is the flow something fundamental and mysterious? There's also a philosophical stance called presentism versus eternalism I hinted at. Eternalism, block universe, says time as flow is an illusion and all times exist. Presentism says only now exists. The past is memory, the future imagination. The truth might be somewhere in between or something we haven't yet discovered. It could be that on the tiniest scales, time loses its usual meaning, like space might in quantum gravity, and something new is needed. However, from our human perspective, time is very real. Even if it were an illusion, it's an illusion we are bound to. We cannot step outside of time to check. We always experience things in sequence. It's much like asking if reality is an illusion. Perhaps at a fundamental level things are different than we perceive, but our perceptions are our reality. In everyday terms, we behave as if time exists. We make schedules. We age. We remember yesterday and plan for tomorrow. The question is delving into the fundamental ontology. Is time a thing or just a concept? One could answer, time is a dimension in physics that allows change to happen and be ordered. Whether it exists independently or is just a facet of other things is an ongoing question. As one physicist said, time is what prevents everything from happening all at once. It's a way to differentiate events. In cutting-edge physics, research like that at the Perimeter Institute suggests that time might emerge from quantum entanglement relations, implying it's not fundamental. If such theories pan out, it would mean at the deepest level the universe might be described without time, and time appears when certain conditions, like lots of particles entangled in particular ways, are met. That's mind-bending, but not any more so than other quantum revelations. In summary, for the second question, while we experience time as flowing and real, there are indications in physics that time might not be fundamental, and that the division into past, present, future might be more about our perception or the special initial conditions of the universe. Some say time really exists as the fourth dimension of space-time, real but different from how we feel it. Others say time is an emergent illusion arising from more basic, timeless laws. This is still unsolved. At an 8th grade level, you can think of it this way. Time exists for us in practical terms, but when you zoom out or zoom in far enough, our idea of time might break down. It could be like how solid objects seem solid, but if you zoom into atoms, there's mostly empty space. The solidity is emergent. Likewise, time flow might be emergent. To conclude our journey, we've learned that time is mysterious and multifaceted. We perceive it subjectively. We measure it with increasing precision. Newton and Einstein gave us radically different views of it. It has a one-way direction tied to entropy. Quantum mechanics hints time might be deeper than we thought. Our bodies run on internal clocks attuned to the day. Time travel is a one-way ticket to the future, with the past likely off limits. And whether time is truly real or an illusion is a question that inspires both scientists and philosophers. No matter what, time captivates us. We live in time, we can't escape it, and we wouldn't exist without it. because time is what allows a change and life is change. As confusing as time can be, it also makes life possible, giving structure to our experiences and a sense of progression to the story of the universe. In exploring these 8 big questions, we see that time is not a simple clock ticking. It's emotional, biological, physical, and perhaps even philosophical. It's a grand mystery we are all a part of. And, as time goes on, who knows what new understanding the future will bring about time itself. Let's hope we choose our time wisely. And yes, that was a time joke.